Do you know how a smartphone works? Or what controls an electric vehicle? Smartphones, smartwatches, electric vehicles, and pretty much any modern appliance is powered by semiconductors. Welcome to the virtual semiconductor experience. On this journey, we'll uncover the incredible story of how compounds as ordinary as sand or silicon dioxide can be transformed into extraordinary semiconductors. We will also see how the latest semiconductor technologies combine elements like gallium and arsenic to make compound semiconductors. Let's begin. Why do we find ourselves in the middle of a vast desert, under the scorching sun? Well, to make semiconductor devices or chips, the process often starts with sand or silicon dioxide. This sand is silicon-rich. When exposed to temperatures greater than 1800 degrees Celsius, the sand melts. The oxygen can be removed, and the silicon is purified. Now we have a lake of molten silicon. A seed crystal is dipped into the pure, molten silicon. When the crystal is slowly put away, a rod or ingot of silicon is revealed. This ingot can then be cut into individual wafers. Push the button to start the process. These wafer substrates are typically very thin, less than 1 millimeter thick. Wafers can be much thinner, made to suit different semiconductor applications. Silicon wafers can then be processed into silicon chips. More on that later. To make compound semiconductors, we have to grow even thinner layers of more exotic semiconductor materials on top of the wafer substrates. This process is called epitaxy. Each epitaxial layer can be just a few atoms thick, with some devices requiring up to 100 different layers. Compound semiconductors can be grown on silicon wafer substrates or on substrates made from compound semiconductor materials themselves, like gallium arsenide or gallium nitride. The epitaxial wafers can then be processed into devices. Now treated, the wafer has to go through a series of steps including photolithography, ion implantation, etch, and deposition. In the photolithography process, a mask is placed over the wafer. This mask contains the desired device pattern. UV light is used to transfer the pattern onto the wafer. Let's go down onto the wafer to see this happening. Press the button. Now we are on top of the wafer and under the mask. Let's turn on the UV light. The photoresist on the wafer changes its physical properties when exposed to UV light. We can dissolve some of the photoresist by using a developer solution, leaving the desired pattern on the wafer. Now let's move on to etching. Etching removes some of the exposed semiconductor material using either a chemical agent or a reactive gas called plasma. In modern semiconductor processes, plasma etching is replacing wet chemical etching. Plasma etching, also known as dry etching, is cleaner and more precise. Now let's take a look at deposition. Press the button. Deposition adds materials like metals or insulators onto the wafer surface. The combination of epitaxy, lithography, etch, and deposition are used to build up semiconductor devices like transistors or lasers. Transistors are tiny switches, and there can be billions of them on a single chip. Let's zoom back out to see the whole wafer. Now we have processed our wafer, it is time to cut or dice the wafer into individual components. This can be done with a conventional saw or laser. We can, however, use the latest technology such as plasma dicing to cut the wafer into individual die or chips. Plasma dicing wastes less space on the wafer and gives a precise cut and a smooth finish. The components are then packaged up and integrated into circuits to power electrical devices. Welcome to my garage. It's unbelievable how many semiconductors are around us every day. They are in almost everything. Compound semiconductors are being used in more and more applications, from communications, 5 and 6G technologies, solar cells, electric vehicles, and much more. Take a look around. Press the button to reveal all of the semiconductors that can be found here. Now you can see there are semiconductors everywhere. Thank you for joining me. I will take you back to the main menu.